This talk is given by Dr. Brian Kirby from US Army. I just want to say that this talk is not recorded because it's from US Army. Top secret, right?
Yes, they have very strange rules, but what can and can't be recorded. So thank you, Lee. So yes, I've worked with Lee for a few years now, and I'll talk a little bit about the work that I've done with Lee. But for the most part, I'm going to talk about some of our work in the last few years trying to apply classical. Hello. Can you hear me? Too quiet? Just me talk louder, or does the mic need to be louder? Okay, I'll be louder. Okay. So I lead a team at the Army Research Laboratory focused on quantum networking. And at the very end, I'll talk a little bit about quantum networking and kind of how the Army research ecosystem works and how we support researchers within and outside of the United States. But today I'm going to talk a little bit about sort of like a side project of mine over the last few years. I started around 2019. This is when I started seeing machine learning popping up, at least in the papers that I was reading on quantum information science. And just as a way to educate myself about it, I was looking for problems that I could apply it to as a way to learn about it. And so the first problem I really kind of spearheaded working on this with was quantum state reconstruction. So I'll talk a little bit about that and then some of the side problems that took us through as we learned more about it. This is probably not as useful now as machine learning has become so popular. Everyone's familiar with the terms, but just to make sure we're all on kind of the same page to begin with, when I say AI, I mean all sorts of systems, expert systems, all sorts of things beyond machine learning. When I say machine learning, I mean that I'm looking at areas where I have a lot of data. I'm trying to learn something from the data and then apply what I learned to other problems. Within machine learning, there's a couple of different paradigms. So supervised is most of what I'll be talking about. This is where my training data is labeled. So I get examples and I know if they're right or wrong. In this cartoon, I know if my examples are on one side of the line or the other side of the line, for example. That'd be supervised machine learning. We've dabbled in unsupervised and reinforcement. So unsupervised is where you're given a bunch of data, but it's not labeled. You want the machine to label it for you, for example. And reinforcement learning is more like exploring a landscape, almost like a video game. We have work in those areas. I'm not really going to touch on them too much today. Most of what I'll talk about today is supervised machine learning. And then within this paradigm, I'll talk about a few different approaches, but mostly I'll be talking about artificial neural networks. These are very simple systems in some sense where you have inputs, you have them multiplied by weights, and then they go into a function and they give you an output, and you just do this over and over and over again. A few things I want to point out about this though that make it really work. One, finding these weights is kind of the whole problem, right? So you have a bunch of examples, you want to back propagate and find these weights. And once you have the weights, you can perform the forward propagation very quickly. The second thing is this function, this activation function, what's important about it is it has to be nonlinear. If it were just a linear function, then no matter how many layers you have in your neural network, it just collapses down to effectively a single layer and can only simulate linear functions, linear transformations. So what's important is that you have some sort of nonlinear function here. We usually use ReRu, but it doesn't matter. There's a lot of advantages, disadvantages to different ones, especially if you're trying to calculate things. You might want to use ones based on exponentials, so you can take derivatives easily, for example. So there's a bunch of different architectures. So for example, here would be like the most basic architecture. These are the input layers, these are the output layers, and then any layer that has no direct interface to the input or output we would call hidden layer. If you have a bunch of hidden layers, we would call it a deep neural network. And then something we touch on occasionally for denoising is something called an autoencoder. So you can think of this kind of like a PCA, like you have data, in this case, of 3 dimensions. I artificially force it down to being represented by only 2 dimensions in the middle, and then expand it back out. And so I'm sort of forcing it to find a lower dimensional encoding. And so we use this often for denoising. So for example, as I talk about, like if we have noisy measurement data, we might feed it through an autoencoder and expand it back out to get rid of some of the statistical noise. And then what I'm really going to focus on is convolutional neural networks. So these are very common in image processing. And just since I'm going to use them so much, a little bit more of a specific example. So if I wanted to convolve this image of where I work, the DevCom Army Research Laboratory, and let's just make it simple. If there's something in the box, I'll put a 1. If there's nothing in it, we'll make it a 0, right? The way convolutional networks work is you find these kernels or filters. In this case, a very simple one, just the top passes through, the bottom zeroes it out. And you walk these across, and these are all variables, how many steps you take between, how big the filters are, all of these are variables that you can change. And you map it to a feature map. So in this case, we have 3 1s in this corner, goes to 3, we have 4 here, goes to a 4, nothing, nothing. And then we further compress through max pooling. There's a lot of other options, but max pooling is you just take the largest number. And what you could think of this as is I'm looking for whatever feature is in my image in this case that this represents. Again, I just made this up, but this could be like an edge or something that I'm looking for. And I compress it down to just telling me if it's there, not where it is. So that's what you can think of the max pooling doing. We're just looking to see if the feature represented by this kernel is somewhere in this figure. I don't care where. I'm going to keep compressing it down and just see if I have it. And so in this way, and I'll go into it, we're going to apply this type of paradigm to reconstructing quantum states. So let me back up now and talk a little about quantum state reconstruction, which I think probably this audience is pretty familiar with. But if I want to do quantum state tomography, generally how this works is I have some sort of source of quantum states that's unknown. I want to characterize it. It can prepare the same state over and over and over again. I don't know what it is. I perform a series of measurements totaling to a complete basis. And at this point, the quantum part of the problem is finished, right? I've taken quantum states, I've turned them into a list of measurement results. And here's the problem that I'm interested in. How do you get that list of measurement results and find the quantum state most consistent with it? So that's the problem that I'll be talking about. There's a bunch of ways commonly that you would approach this problem, right? The simplest and least accurate would be something like Stokes reconstruction or augment it with linear search, where you just take the coefficients, you just take the measurement results, and those are just the coefficients of the operators, and you add them back up to get the original state. Problem with this is that it's not constrained to be physical. You often get non-physical states. It's very inaccurate if you have any noise. The next level up, slightly more difficult to calculate with maximum likelihood. The problem with this is it's a little bit biased towards low rank reconstruction, but also has no natural error quantification. So you have to sort of ad hoc quantify the error, maybe by running it multiple times, for example, but it's not ideal. Kind of the gold standard and what we try to apply whenever we can is Bayesian mean estimation. So this is I have some prior distribution over which I think my state comes. I take the data in, I update that prior distribution, and then I take the mean of it, and that is my reconstruction. This is very hard to compute. I'll talk a little bit about why, but what's great about it is it's provably the approach that minimizes the mean square error. So whenever possible, we try to do that. So where does machine learning fit in this? So our goal here is to kind of flesh out this landscape a little bit. We want to get something about as accurate as maximum likelihood, but we want it to be much faster. And when I say faster, I mean the goal was after learning. So our goal going into this is noticing that every single time I want to reconstruct a quantum state, which in our labs can be 10,000 times a day, for example, we have to run the entire maximum likelihood search every single time. And so what we were thinking with machine learning is what if we front load a lot of that difficult computation into the training period of training the neural network, and then we can perform the inference every time thereafter very quickly. And so this is kind of our goal, our naive goal when we went into this, was just trying to get something about this accuracy, but not as hard to compute. I'll also talk about how we've used this as kind of an intermediate step in more complex reconstruction methods, such as Bayesian mean estimation, to kind of reduce the complexity, make them converge more quickly. Okay, so let's jump to the punchline. You can do this. I wouldn't be up here talking about it, right? So here's like the most basic proof of concept. This is for 2 qubits. Usually you do 36 total measurements, 6 by 6 measurements, putting it through a convolutional neural network and dropout layers and all these things. The point is you end up with the Cholesky decomposition, which you can then multiply back into a full density matrix. And the reason you would do Cholesky decomposition is that this constrains us to only reconstruct physical states. So it's impossible for us to reconstruct a non-physical state because we're immediately guessing an intermediate step here. So just to give you a sense of how accurate we can get, for a single qubit, we can get to 4 nines of accuracy on average, which is very high. For 2 qubits, over 9.9. And really the problem is just how much time are you willing to spend, how much computer are you willing to throw at the training is really the biggest issue here. But to give you a sense of kind of the accuracies we're looking at. So in working on this, we came to all these kind of interesting side questions. And so number one, how does this cope with experimental noise, for example? The second one, how does this scale? Like, is this sustainable? What if I want to go to 10 qubits? Like, is it even possible to train something that large? The third is, how would you incorporate prior information? A lot of these other paradigms are very natural ways you would incorporate a first guess into your reconstruction. It's not so clear how you would do that here. The fourth is, what if we only have a few, copies of this state? Or fifth, what if we're missing measurements? It turns out for both of these, there's a lot of existing machine learning tools you can apply. And then 6, can we use this as an intermediate to other more sophisticated approaches? So I'm not going to talk about 1, 4, and 5 because I think they're kind of straightforward applications of standard machine learning. Where I think the more interesting physics comes in is 2, 3, and 6 here. So starting with 2, how does this scale, right? That's kind of the immediate question that we all have. As expected, the training, so this is qubits along the bottom axis and time, just real time on a laptop computer on the y-axis. In pink here is the reconstruction time, so the inference time. So you can see it barely increases from 1 to 4 qubits, 0.77 milliseconds up to 0.8 for a 4-qubit reconstruction, which is pretty fast. But the training, as we expect, scales at something seemingly exponential. This is for 1 epoch. Normally we're doing 1,000 epochs or something. Maybe more enlightening is just look at the trainable parameters. So what is the size of the network we need to reach the same level of accuracy? It starts to explode pretty fast. So in some sense, this is depressing, but again, we only need to do the training once. So as long as we can get over this hill one time, the network will always perform inference just as quickly. The second problem is this is actually 4 different networks, right? I have to train a network for 1 qubit, I have to train a network for 2 qubits, et cetera, all the way up to whatever dimension I want. This seemed like an insurmountable problem until we realized that we can just make these adapt to dimension kind of in a straightforward way. As long as I have a network trained on reconstruction of any system larger than the system I actually want to reconstruct, I can just trick it with simulated data. In this case, we just do fluid mixed state, but you can just append the simulated measurement results, do the reconstruction with the larger system, and then trace back out all of that simulated measurement results you put back in the beginning and get back the state that you actually want. There's a lot of theoretical reasons to think this works quite well, actually, because of the monotonicity of the fidelity. So as long as the fidelity of your larger system is quite large, it's always going to be pretty good at as you trace it down to smaller systems. And so really, what this shows us is that we only need to train the system once on whatever the largest system we can possibly get to is, and then we can always do all of the systems smaller with that same network. Okay, the third question here is how do we incorporate prior information? So this ended up being quite an interesting question for us. We train our networks on synthetic data, right? That way we remove all the noise from it, all the experimental noise from it. So what this means is that we randomly sample Hilbert space somehow, we simulate measurement results on it, we use that as training. The question is, how do you choose those states that you randomly sample? We initially started choosing them through trying to fair sample something like according to the Hilbert-Schmidt metric or the Beers metric, some sort of fair sampling of the Hilbert space. The problem is most states, as soon as you get out of a few dimensions, are incredibly mixed, right? And very far from the states you actually encounter in experiments. So here's a distribution for a single qubit. You can see like the distributions according to purity are very broad. And so you're sampling kind of over the whole Hilbert space. And a lot of the experiments that you're doing are probably like 0.9 fidelity or something. You're covering them up quite well. The problem is once you get to like 10 dimensions, all of your states, as you randomly sample them, are incredibly mixed. And you can sample 10 million states and probably not even get one near fidelity of 1, which again, in most experiments, we're not fidelity 1, but we're also probably like fidelity 0.9 or something, right? So the problem is there's a huge mismatch in random sampling fairly in the states that you actually see in experiments. And so what this means in practice is very similar to Bayesian mean estimation. If you start with a prior distribution that's way different than what you're expecting, what you actually see, it just takes a lot of time. It takes a lot of measurement results. It takes a lot of time to converge. In our case, what that represents is it just gets us further from the right answer. So our network is just a lot less accurate if we're only training on states that are very different than what you actually find in an experiment. So to deal with this, we started looking at for other distributions that don't necessarily fair sample, but can be concentrated in different parts of the Hilbert space. So Maya and Opera looked at this interesting distribution that we found where it's hard random pure states and the coefficients come from the Dirichlet distribution. And what's interesting about the Dirichlet distribution is that it has all these tunable parameters where you can change the density of them. So the global feature of these Dirichlet parameters. So 111 would be like the fair sampling, right? Like just like the Hilbert-Schmidt distribution. But I could make it very mixed. I could make it focused on the edges, which the analogy here would be like the very pure states. I have a lot of control about how I bias this. And so we ended up using this to create custom distributions for training that better mimic the experimental scenarios that we're going into. So here, for example, is us just taking random date sets on the IBM queue and then just putting them, plotting them according to purity. Here on the right is what you actually get, like if you just do it yourself. On the left is what IBM Q will tell you get once they like subtract out all of these zero counts and all these other kind of tricks. Either way, I can just bias this MA distribution to really well cover the actual experimental scenario, whereas here's the Hilbert-Schmidt and Beers, right? I mean, I could train on this millions of times and never even see a single state that's actually represented by the experimental scenario. So in practice, this has a couple of nice use cases for us. One, we can train our network to be somewhere balanced between reconstructing pure states very well or reconstructing mixed states very well, depending on what situation we're expecting to go in. Probably optimally, we want to go somewhere that perfectly balances the two. It's not perfect at either, but the mixes between them. You can also use these as prior distributions in Bayesian mean estimation. And here we show, for example, you can reduce the time to convergence of Bayesian mean estimation algorithms by using a distribution that better matches the experimental scenarios. So much time we have. Okay, and then finally, can we use this as more of an intermediate protocol in larger, more sophisticated protocols? Because really, at the end of the day, we don't have any error guarantees, right, for machine learning-based reconstruction. So the power of it is that it's very, very fast. It gets you relatively close to the correct answer, but you're probably not going to use that in a fundamental physics problem where you need a guarantee on how accurate it is. So what if we kind of combine the best of both worlds, right? We take Bayesian mean estimation, which again is provably the one that minimizes mean square error, and instead of using it to do the full reconstruction, what if we just use it to get Bayesian mean inference closer to the right answer to begin with? So instead of using something like a flat prior, a Beers prior, Hilbert-Schmidt prior, what if we use the machine learning system to create a custom distribution based on the measurement results and then use that as the prior distribution for Bayesian inference? And what we found is that, so here's an example of like what this might look like in practice. Here's the experiment, like from the IBM Q, for example. Here's the ML produced prior. It starts to overlap quite well. It's pushed the Beers and Hilbert-Schmidt priors closer to the experimental scenario. And so in practice, what that means is that it just converges faster, right? The Beers prior will get there eventually, that provably it has to. It just will get there much slower. And even taking into the added inference time of the machine learning system, we still end up net reducing the time for convergence. So it's a net win, even with the extra inference time of the machine learning system. So everything I talked to at this point was full state reconstruction. So if I have an entire, I want to completely reconstruct the density matrix. I want to find out everything I can possibly know about the state. But a lot of times you don't care about that, right? You just want to know certain features. For example, is it entangled? Is it pure? All of these kinds of things. And one approach spearheaded by Lee and her students Alex and Aiden here at University of Toronto was looking at the close relationship between support vector machines and entanglement witnesses. So if you're not familiar with entanglement witness, it takes advantage of the fact that the separable states in Hilbert space form a ball. And so you can always draw a hyperplane between that ball and any pure state. And then you can just check if the state that you're measuring is on one side of this plane or on the other side of the plane. Interestingly, this is quite similar, conceptually at least, to what a support vector machine does. A support vector machine in machine learning, you give it a bunch of data, you tell it to draw the hyperplane between that data that maximizes the margin, right? So what Alex and others and I only lightly helped, so most of the credit goes to Alex and Lee, was to apply this paradigm by sampling the space and then using an SVM to automatically define the entanglement witness for you. And so here's a few examples. What's really nice about this is that you can also use recursive feature elimination to just automatically, not only can you automatically define the witness by sampling the space, you can then automatically reduce the number of terms in it using recursive feature elimination. And of course, that comes at this cost of noise tolerance, but sometimes that's fine, right? Sometimes that's okay. You're okay trading off the noise tolerance to have a much simpler experiment. So that was another place that we've applied machine learning. I'm going to take a short detour to talk about a closely related but non-machine learning project is characterization through randomized measurements. And the reason I wanted to talk about this is there's been so much talk about classical shadows here over the last few days. This is a closely related paradigm but slightly different in that we just like shadow, care about our local measurements being hard random. However, we don't track them. So all I need to know, I just have to be guaranteed that my local measurements are hard random. From that, I can extract the local unitary invariance of the density matrices. And from those, I can calculate a lot of things I actually really care about, like violations of the CHSH inequality or purity or any of these other basis invariant properties. So this approach was originally developed at University of Siegen by Alfred Grunhe, and we applied it to 2 qubits. And in our labs, we looked at, first of all, can we actually make the measurements as random as you need, as quantified by the frame potential? This was harder than we thought it would be, to actually make them as random as we needed them to be. But once we had them random, this is showing 3 of the invariants across many, many experiments. And we showed that you can provably show that you're violating Bell's inequality without any local basis information. And so the use case and what we're implementing this on now is deployed fiber, where we don't want to have to worry about stabilizing the polarization, the local polarization states, the local polarization bases. We can then just further randomize them, right? Just kind of fold in the randomization of the polarization bases into the approach itself. So I just wanted to advertise this one since it's very similar intuitively to classical shadows, but a very different paradigm. Okay, another place that we've looked at applying machine learning, classical machine learning in quantum information science has been to IQ modulators. So this is the work of my colleague Dash Vittorio at the Army, and then Dirk England and Hugo Leroux at MIT. So to be clear, I did not develop this part. They developed this very nice lithium niobate IQ modulator. It takes in the light, it gives you complete control over the phase and amplitude of the light that comes out. It's ultra low power. It can be used for coherent communications. The question is, and the problem is, you have 2 knobs, right? You have voltage 1 and voltage 2. And this allows you to completely control the encoding, the phase and the amplitude of the light that comes out. The problem is the mapping between the V1 and the V2 that you put in. So this is like a nice square grid that you would put in, for coherent communications. What you actually get out is this huge mess, right? And so the question was, how much information can we actually, use this system for when the mapping between input and output is so complicated? And so we looked at 2 different approaches. One was first we optimized on the encoding side. So here's the unoptimized approach. You can see the lines follow the same lines as here. And this coloring is the phase. So as long as you're around one of these phase minimums here and here, then you get 2 pi phase around the circle. And so you can use that for encoding. So we used Atom Optimizer to optimize the encoding, essentially minimizing the overlap of all the output distributions. And this bit error rate, don't think of it as actually like a communication bit error rate. It's just a benchmark that we're using to see how well this is working. We go from 6% bit error rate to 0.875 just by optimizing the encodings. And then further, we looked at, can we then add to that even more and optimize the decoding using machine learning? So in this case, we train a deep neural network that essentially learns the transfer function, the noise properties of the transfer function. And that's essentially intuitively why it outperforms just kind of, can't think of what it's called, the centroid method, where you just take this distribution and this distribution, and you just pretend they're Gaussians, you just draw a line between them, and that's how you decode it. We can outperform that using machine learning, essentially because we learn the asymmetries of the noise as it goes through the transfer function. And so here, blue is the centroid method, and then we get a slight modest improvement across the entire range of noise that we looked at by further using the deep neural network for output. So we use machine learning on the input, machine learning on the output, and we can greatly increase the overall throughput of the system. One other place that we've used machine learning in our research has been, and I forgot to put it, this is with Tulane University, Ryan Glosser's team down at Tulane University. We've looked at using machine learning as hopefully an approach to replacing some physical optics, in particular for decoding on-off keys that go through turbulence or go through thermal noise. So first of all, this is the experiment that we did, but intuitively,